case, we're looking at 9.1 Master Learning Objective. I can use exponential growth and decay models to solve real-life problems. Hold on. Sorry. So, you've seen exponential growth and decay models before. You saw them in Math 1. So this should be review. So just a little bit of vocabulary as we get started. An exponential function is a function where the variable is in the exponent. For example, right, y equals anything, so usually like a to the x, right, where a is just a number, so y equals 2 to the x, 5 to the x, right, that's an exponential function. Okay, then we have exponential growth. The rate of change is positive, right, exponential growth is when the rate of change is positive. And really, we have exponential growth when your base is greater than 1. Okay. So, for example, our base here is a, so whatever is being raised to the exponent. Okay. Decay is just the opposite, right? The rate of change is negative. And we don't want to say the base is just less than 1. Really, the base is between 0 and 1. You don't ever have a negative base, because then as you do a power, it's going to switch between positive and negative. So, for example, right, negative 2 squared equals negative 2x. Just to quickly draw this, negative 2 to the 0 is 1, negative 2 to the 1 is negative 2, negative 2 squared is positive 4, and then go down to negative 8. And so you see, like, it's doing this thing like this, and when it's just bouncing back and forth like that, it's called an oscillating function, and it's not actually a function, okay? So our base can't be negative, so it's between 0 and 1. Alright, so then we have our exponential growth models and our exponential decay model. They're very similar, with one small difference. Our exponential growth model is y equals a times 1 plus whatever your rate is, if it's growing by 5%, 10%, 100%, whatever. So 1 plus r to the x, where your decay is a times 1 minus r to the x. And so this just makes it more than 1 and less than 1, so that it fits what that base should be. So then a represents your initial value. So whatever you have at the beginning. And R is your rates of growth or decay. And most of the times with word problems, you just have to really read to know which one it's going to be. So if it says like it's increasing or it goes up, right, it's going to growth. Decreasing, depreciation is a big word we'll see. That also means going decaying or going down. Okay, so kind of from your word problem, you can determine which of those it's going to be. Alright, examples. Determining if each function below is exponential growth or exponential decay. then identify the growth or decay factor. Okay, so we want to see if what our base is. So 4 is being raised to the power. So 4 is our base, and that's greater than 1. So that's growth. So that means 1 plus r equals 4. Ahead of myself. 1 plus r equals 4, so r equals 3. Sorry, I said 4 and then jumped to the next step. Now, we usually write our rates as percentages. So this is 3. There's a decimal here. We still want to move it twice so that we have placeholders. So this grew by 300%. Okay, so here, our base is 2/3, which is less than 1. So that's decay. So that means 1 minus r equals 2/3. Solving for this, you'll kind of get better at these as you go, but we still need to kind of look at it, right? Subtract 1. So r equals 1/3. So I'm really just solving for r. I'm going to put it in decimal. Oops. So r equals 0.33 repeating, right? So that's 33% when I move that twice. Okay. Or you can times it by 100. That also helps you think, right? Percent is per 100. So that's 0.33, right? We multiply it by 100. Okay. Here, what's being raised to the x? So now, right, this has a number out in front, but that's not part of my base. Okay, the base is just what's being raised to the power. This would be like your a value, which we're not concerned with right now. We'll look at that in the next examples. So we have 0.25 as our base, which is less than 1, so this is decay. So 1 minus r equals 0.25. Subtract 1. Negative r equals negative 0.75. Which is then 75%. Right, so again, subtracting, right, is negative r and negative, so we just get rid of the negative, right, or think of it as dividing by -1. And again, this moves over twice, or we multiply it by 100 to get that percentage. Last one for this section. Again, this 0.05 in the beginning is not what's being raised to the power. Again, that would be considered our a value. So 1.5 is greater than 1. So that's growth. 1 plus r equals 1.5. Subtract 1. R equals 0.5. 0.5 is 50% because we still have to move it twice. Or again, 0.5 times 100 is 50. So be careful with switching from decimals to your percentages. All right, go ahead and turn the page. So now we're looking at some word problems. So example 2 says the value of a car B in thousands of dollars can be approximated by the model B equals 25 times 0.85 to the t, where t is the number of years since the car was new. I'm just going to rewrite out, especially because it got cut off. B equals 25. Does this represent exponential growth or exponential decay, right? Well, 0.85 is greater than 1, or is less than 1, so that is decay. Identify the annual percent increase or decrease. Okay, so it's decay, so 1 minus r equals 0.85. I'm going to subtract 1, so I get negative r equals negative 0.15. Divide by our negative, so r equals 0.15. This is a 15% decrease in the value of this car each year. Okay. C, what was the initial cost of the car? So our A value, right, yeah. We have V equals 25, 0.85 to the T. Our initial cost comes from our A value, so that's this. So initial cost $1,000. Again, I put $25,000 because it's in thousands of dollars. A equals 25, the initial cost is $25,000. There's one other question I want to add on to this. So let's write it over here. We'll write a D. How much will the car cost after 10 years? Okay, so that's another common question you'll see. Now that I have this approximation of the cost of the car, the value of the car, I want to know if I go to buy it from this person in 10 years, what's it going to be? So again, I'm going to start with, okay. So 10 years represents my time, which is T. So I'm going to, V equals 25 times 0.85 to the 10th. Then this, there's no variables on this right side, so I'm just typing all of that in my calculator. So I have 25 times 0.85, and let's put that, let's write it exactly like it is, so 0.85 to the 10th. We get 4.92186. Again, but this is in thousands of dollars. So really it's going to be 4,921. Let's round it to the nearest dollar. $4,922. Okay, so in 10 years, that's going to be the value of your truck. Or car. This isn't a truck. Alright, let's look at example 2. In 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. By an exponential growth model, giving the population P in billions, T years after 2000. So, it's exponential growth, right? Because it tells us, but also if it doesn't tell you, the population increase. So that's also telling us that it's growth. So if it just tells you to write an exponential model, which it might, right? Always look for increase, decrease, appreciates, in the terms of like money means you're gaining money, like stocks appreciate over time, or like the cost of your car depreciates over time, right? So those are keywords we can look for. So this is stuff like growth. So our growth model is y equals a times 1 plus r to the x. Okay. So we're doing we're finding the population. So instead of y, we'll use p equals, again, a is our initial value, so what it starts at. This is telling us our starting point is 2000. So in 2000, the world population was 6.09. So that's where our A value comes from. Times 1 plus, R is our rates, right? 1.18%. R equals, I want to go backwards, so that's 0.0118. If you're struggling with doing the other direction as well, again, you can just divide by 100. So if I have 1.18%, if I divide that by 100, that will give me my percent as my decimal. 1 plus 0. And then instead of x, since it's talking about years, time, right, we'll use t. So if I just clean it up a little bit, we get p equals 6.09 times 1 plus. I like that. That's what I'm adding. Right. 1.0118. The adding is really easy because you're just doing 1 plus whatever that decimal is. Or you could add your calculator. Subtracting, you need use your calculator for that as well. Okay. The one thing students always want to do is then multiply these. You can't do this. This one has a variable or an exponent, this one doesn't. So this is our final answer. That's what it's going to look like, right? A times something to an exponent. Now I want to estimate the world population in 2005. So this is giving me a time, but my t is not 2005 because 2000 was my year 0. That was my initial amount. So this is telling me then t equals 5. After 2000. Okay, so that's another thing we have to be careful with. So now I'm just going to plug in 5. And again, we can type that in our calculator. We only have 6.09. 1.0118. We get 6.46 billion people. Make sure we have units. And we're looking at what our units are in. Right, that is it. I'll see you guys tomorrow.